And so my resultant, again, from the beginning to end, where am I relative to where I started? That angle looks to me like about a 25-degree angle. Again, just eyeballing it. And then the length, well, if that is 10 right there, that looks like 25 meters. No, that can't be right. Let's go 21 meters. I know it can't be 25 because that demon was cast out of my head. Since I got 25, I know, or got roughly 25, I know something's off. But at least I have a ballpark figure. If I end up with 130 degrees or end up with 2, I know something is badly wrong. So this just gives me an idea of where it's going to be. But we can do better. Graphing method, thorough attentively. So I established some horizontal line, and I will assume that's horizontal. And I start a starting point. Now it doesn't matter which one I do first. I'm still going to do A first, but it doesn't really matter. The commutative property holds, just like in scalars. 1 plus 2 is equal to 2 plus 1. Vector A plus vector B is equal to vector B plus vector A. 40 degrees. So I got the protractor here. .40 degrees is along that line. I need a scale, 15. So how about if I do 2 centimeters is equal to 1 meter. So 2 centimeters on this is equal to 1 meter. In other words, 15 meters would be 30 centimeters. Already in the stuff there. Now, when I drew the head just then, I'll sort of recreate it. If the end of the head was there, when I draw the head, this is the point where I start. I do not draw my line here, and that's where the end point is, and then draw my head above it. If I'm doing it properly, the head should be at exactly, given our scale, the 30 centimeter mark. Now, this is my new starting point. And it's 15 degrees below my horizontal. Well, I need to draw another line here. I need this to be parallel to this line right here. So the question I'm asking you is are they parallel? I got a nod. I could have some back there, I just can't see. I've got a couple people agreeing, okay.
It's close.
What would I do to do better? I heard close.
Yeah. I can't tell if it's exact.
Okay. And we will go with this. And so now I need 15 degrees below that. And my line's slightly off, so I'm going to keep it up a little bit. And so this line should be 20 centimeters long, given my scale. And so my resultant from beginning to end So my vector is not pointing back towards the middle, just even though I drew it that way. I put the head on here. This would be the direct as the crow flies. How do you get from one place to the other? That's the resultant. I mean, you might have to go, reality, if you're walking, go around blocks and buildings, you generally can't cut through a building, directly at least. And so this would be the as the crow flies direction. So my magnitude and direction of my resultant here, let's get the scale going. That is, looks like 44 centimeters. So that would correspond to 22 meters. This is the actual drawing. And this is reality. Sure, we'll call it that. And then my angle. Oh. And that is 17.5 degrees. So we have our crude sketch right here, and this would be just, you're desperate. A much more retentive one, more accurate, I'm going to bet. And so how do we write this? So let's talk about polar form and rectangular form. Polar form is you have parentheses, magnitude, comma, direction. That's polar form. So the way I would write this problem in polar form is we had 15 meters at a 40-degree angle plus a 10 meter at negative 15 degrees equals, no, I can bother write down the first one. We had 22 meters, 17.5 degrees. So this would be writing this is the problem of adding vectors in polar form. Please note that it is negative 15 degrees. That is a convention that I am assuming. There are a lot of math conventions that you don't necessarily, you can't assume, but I am assuming 0 degrees is that way. Positive angles go counterclockwise. So 0, 90, 180, 270, 360. Going in the other direction, they're negative. So 0, negative 90, negative 180, negative 270, negative 360 degrees. And so since that one went below, that's negative 15 degrees. Questions to here? Because we're about to actually come up with the real answer. All right, rectangular form. Recognize that I have this 15 meter, I went 15 meters at 40 degrees. I could also just get to the exact same spot. I also could have gone to the right a certain amount and up a certain amount and ended up exactly where I was before. So this right here, I go a certain distance to the right and a certain distance up. Well, we just went through that math. Let's try to figure out what these two lengths are. I created a right triangle here. So we are going to break this up into rectangular components. And where I got space. So the math problem is this. And that is a 40-degree angle. That's the math problem. What are my two sides here? Well, the adjacent side is 15 times the cosine of 40 degrees. The opposite side is 15 times the sine of 40 degrees. Which are
11.49.
Is this one?
For cosine.
11.49? Okay.
And 9.64.
One more time?
9.64.
9.64? So the way that I would write that, I guess I have the information over there. Now to express this, because again, I have this 15 meters, 40 degrees, and I'm making the claim I get to the exact same spot if I go 11.49 meters right, then 9.64 meters up. Now, there's a problem with this. I mean, I'm not saying it's wrong, it's just that there's a problem with doing this, and there's another way of doing it, which we're about to do. I assume someone else got the same numbers that she got? Okay. The two problems are, right and up are sort of vague, because if I told you look up, you're not necessarily going to be looking in a direction someone's going to walk. You'll be probably looking that way. Up is only relative to the board. The other problem is, why am I writing the whole word out? This is physics. Sure, I don't want to write that out. So many letters. So they came up with a way of doing it. It is known as the unit vector. It is a vector, so it has a magnitude and direction. The magnitude is 1. No units, just 1. So the magnitude is 1. Unit vectors always have a magnitude of 1. The direction at this point is whatever I say it is. Whatever I say it is. And you too will have this power that you can declare what these things will be. Now there are certain boring conventions. Some textbooks will use the unit vectors of x and y. I don't like that, because in math class, which way is the x-axis?
Horizontal.
Why? No, oh, sorry, the question why. Why is the x-axis horizontal?
I don't know, someone said so a long time ago, and it stuck.
Yeah, somewhere along the line, the math people said, "Oh, I'll just make that x, let's make that y." There are times in which we don't want that. There are times in which we want our coordinate system not to be like this, but to be like that, because it's going to make the math a whole lot easier. And we want to make the math easier. Especially when we get to chapter 4. That's when we're really going to start getting into how do we want to change our coordinate system so that it makes life nicer. So instead of using x and y, because I use ij. And that's not just a me thing, there are a great many textbooks that do the same thing. So what I'm going to do, instead of right, I'm going to say I hat. And that's the symbol for a unit vector, is the hat. If you use Open Office Formula Writer, hat is the key word. We're putting that symbol over it. Could have made I hat any direction I want, but it's convenient because I'm going rectangular coordinates. Well, I gotta pick some direction for I. J hat, if you're doing rectangular, does have to be perpendicular to it. So up or down, it doesn't matter. Pick one. Which way do you want J hat to be, up or down?
Up.
All right. There are advantages and disadvantages to doing that. So now I can write this as 11.49 meters I hat plus 9.64 meters J hat. I am contending that this is the exact same as this is. They are equal to each other. Thus I wrote an equal sign there. Just one's polar form and one is rectangular form. This is rectangular form right here. Questions to hear, because we're about to do the other vector. And by the way, for a problem, do not automatically assume that's I hat and that's J hat. This is what was defined for this problem. I decided on I hat just because I was forcing it. J hat was decided by Amy, at least that was the voice I heard. So, don't assume I hat and J hat. So when you're writing a problem, if you're doing a master set, or you're working on a test, and you're using I hat, J hat, define it. Just write it up there. If you do it at the top of a test, I'm assuming it's true for the entire test unless you tell me otherwise. If you do it at a problem, then I assume it's true for that problem. For those who do computer science, that would be a global variable and a local variable. All right, let's do the next one. So it was down like that. It was 10 meters, 15 degrees. Since my coordinate system is horizontal and vertical, then I need to break it up into horizontal and vertical. So this will be 10 meters times the cosine of 15 degrees. This is 10 meters times the sine of 15 degrees. So I just wrote numbers down. I don't know. What are the right answers?
10 cosine 15 is 9.66.
6.
And for sine 2.58 or 59.
2.5. So this is A right here. So who wants to take a shot at telling me what vector B is in rectangular form? So when we first write polar form, that was 10 meters and negative 15 degrees. All right, in rectangular form?
Would be 9.66 meters I, or what's that called?
I hat.
I hat.
Hat, you know, like something on the head.
plus 2.59 meters J hat.
Right, one small mistake. You said exactly what I was expecting you to say at this point.
Negative.
Would be
Yeah.
negative.
Because J hat is defined as upwards, but this goes down, you need to somehow indicate that it's going the opposite direction, and so minus. And so I've now taken my problem here, and it is 11.49 meters I hat plus 9.64 meters J hat plus 9.66 meters I hat minus 2.59 meters J hat. Now I'm writing meters in here because they really are there, but when you're solving a problem, I know my answer is going to be in meters. My magnitude will be in meters. I don't have to write units as I go, as long as I know what's going to end up being. Now we're not done yet. This is A plus B. Now how do you add these?
You add the I's and you add the J's.
Just like in Algebra 1, if this were 11.49x and 9.64y, 9.66x minus 2.59y, you add you add the,
Combine like terms.
sorry,
We combine like terms.
you like terms, there we go. It's blanking, all right, senility is kicking back in again. So 11.49, 9.66, doing the fancy math here. 21.15. So I get 21.15 meters I hat plus, well, now I do the J parts. 7.05. Now, I didn't specify what form I wanted the final answer in, and if I don't specify, then, well, that's fine, you can leave it there. We are gonna keep going, but that is a legitimate answer to the problem. Questions to hear before we see how close we were when we did it graphically. I should erase this sort of question. Okay. To find out how close we were, we either need to put this into polar form or put that one into rectangular form. So let's put this into polar form since we've already done a polar to rectangular. So my final answer is, I'm saying that we went over 21.15 meters to the right in the I hat direction and 7.05 meters up, as J hat is up. My resultant, here's my resultant. So I need to know the magnitude of it and the direction. The direction is defined unless it's stated otherwise, assuming 0 here and then positive angles going this way. So 0 that way, going this. So I want to figure out that angle there, and then I will just show a lack of imagination and use theta again. So to find the magnitude of R, the Pythagorean theorem, it's somewhere around 22.
.29.
Oh, that's R. And now the angle, all right, so I've got 3 sides here. Because we now know this is 22.29. I'm assuming you rounded off when you told me 22.29. Okay. So I have 3 numbers here, this had some rounding in it. That had some rounding in it. This has a little bit more rounding because this is based upon two rounded numbers. So traditionally, you should use tangent here because tangent is going to use the two side lengths that have a little bit less rounding involved. On a quiz or test, whatever way your mind's working at that time is fine. But if we want to be a little bit more precise about this, we should use tangent. So the tangent of theta is the opposite over the hypotenuse. So theta is the arctan of 7.05 over 21.15.
$18.435. It's actually 4349 something.
Meters.
But at least you knew what I'm doing here.
Degrees, right?
Degrees. It's an angle. For angles, if you do not tell me the units, it is assumed radians. Radians is the one unit that you can put in or take out, whatever you feel like. So putting this back into polar form, we have 22.29 meters, comma, 18.4349 degrees. It's not too far off, considering the graphing method is, especially with fat markers and on the board. And hey, is this parallel? If you ever have to do it graphically, adding vectors graphically, I strongly suggest graph paper. There's a lab that I do most semesters, but not every semester, in which you would actually do that. Questions? All right. So if I did 15 meters, 40 degrees, minus 10 meters, 190, no, that's not what I want. 165 degrees. How do you deal with subtraction? What does the negative mean? Well, let's draw these two vectors up. Maybe that will bring it up. Let's see, get a coordinate system here. So 15 meters, 40 degrees is roughly something like that. So that's 15 meters, 40 degrees. And 10 meters, 165 degrees. It's going that way. It's 10 meters, 165 degrees. What does a negative vector mean? I keep saying negative vector and it looks like subtraction. Let me just rewrite this. 15 meters, 40 degrees, plus negative 10 meters, 165 degrees. Okay, so now what does a negative vector mean? We dealt with this already.
Is it just flipped over the axis?
Yeah. Negative just means the other way. So instead of this vector subtracting that vector, we're just adding the opposite. And we've already done the problem. This is a vector that's completely opposite direction to this vector right here. Yes.
What were we solving for when we did the tangent?
The
18?
resultant is a vector, so it has magnitude and direction. And so magnitude Pythagorean theorem, and direction is what we were trying to find here. So theta, so based upon, theta is the angle based upon 0 degrees here. It's the angle from 0 degrees. And so the direction piece. Wasn't sure if the nod just then was the, I answered your question?
Yeah, you
or-
did.
Okay. It looked similar to the way it seemed in my mind when I was a student. I just wanted the teacher to stop.
That's good.
All right. We've done addition, subtraction. Again, subtraction is just saying adding the vector going in the opposite direction. We now have multiplication. I'm just going to bring up multiplication quickly. We will go into multiplication in more detail later. But there are two ways of multiplying vectors. So this is just sort of an introduction. You know what, actually, let's take a 5-minute break, stretch legs, come back, and just something to anticipate. Dot products, cross products. Yes. And you thought the world that today would not get as exciting as it's going to get.